The directional rotation of a three-phase motor may be reversed by interchanging any two of the three leads feeding the motor. However, NEMA standards require that lines 1 and 3 be interchanged. If the motor is to be controlled by magnetic devices, then reversing starters are used. Reversing starters consist of two 3-pole contactors. Each contactor will have a set of normally open auxiliary contacts and a set of normally closed auxiliary contacts. They will both feed a common overload assembly. The normally open auxiliary contacts will usually be used to provide seal-in, while the normally closed auxiliary contacts will be used to provide a means of interlocking. There are three methods of interlocking for reversing controls. They are auxiliary contact interlocking, push-button interlocking, mechanical interlocking. Mechanical interlocking is usually factory installed or may be added in the field by retrofitting a kit to the contactors. Interlocking is necessary to prevent both contactors from being energized simultaneously. Their coincident operation will cause a phase-to-phase short. This will result in burnout and possible injury. The diagram above shows the graphical representation of mechanical interlocking. The first coil to energize and cause the armature to move will shift a lever that will physically prevent the other coil's armature from moving. By blocking the movement of the other coil, burnouts and phase-to-phase shorts are prevented. Leaving the blocked coil energized for extended periods will cause damage to the coil due to improper inductive reactance. Push-button interlocking is an extremely effective electrical method of preventing both the forward and reverse contactors from closing simultaneously. This method uses double-circuit push buttons to accomplish the interlock. The normally closed positions of both the forward and reverse buttons are in series with the opposite coil's seal-in contacts. Because of this arrangement, it is possible to change the rotational direction of the motor without stopping the motor first. This is not recommended. This method of interlocking will also eliminate the possibility of racing. If both the forward and the reverse buttons are pressed at the same time, neither coil will energize. The most common method of interlocking for reversing controls is auxiliary contact interlocking. This method uses a set of normally closed contacts to prevent simultaneous operation of both contactors. When the reverse coil is energized, it will open a set of normally closed contacts that are in series with the forward coil. This will prevent current from reaching the forward coil. The same scenario is true if the forward coil is the first to be energized. The stop button must be pressed to change the rotational direction of the motor. This application shows limit switches in series with each coil. Control circuits similar to this are used in applications where over-travel of a mechanism could be dangerous or cause damage. A typical application is an overhead door in a warehouse. If either coil is energized and the mechanism opens the limit switch, that coil will de-energize. The system can only be started in the opposite direction. In this demonstration, the stop button is disabled. However, it is important to never disable any stopping device. NEMA defines jogging or inching as the quickly repeated closure of a circuit to start a motor from rest for the purpose of accomplishing small movements of a driven machine. The circuit shown above uses the lock-stop method of jogging. This will entail mechanically locking open the stop button to prevent seal-in. If this method of jogging is used, it must be clearly marked. While extremely effective, this method is not commonly used in industry. This circuit uses a two-position selector switch to select a jog or run mode. If the selector switch is in its closed position, a normal 3-wire control circuit exists. If, however, the switch is placed in the open or off position, the start button will jog the circuit. This method of jogging is very widely used in industry. A two-circuit push button is used in this diagram to provide a means of jogging. This circuit will operate as a normal 3-wire control if the run and stop buttons are used. By pressing the jog button, the normal current path is opened, removing the seal-in from the circuit. An alternate path is completed around the run button and the seal-in contacts. This type of jogging circuit is potentially dangerous. If the jog button is repeatedly operated rapidly, a seal-in can occur. Careful choice of the two-circuit push button can eliminate this possibility. Push buttons that make the normally open contacts and break the normally closed contacts at the same time will create this hazard. The two-circuit push button shown in the diagram breaks the normally closed contact before making the normally open contact. Use of this configuration of push button will eliminate this possibility. Many industrial applications use control relays to ensure that a machine operator has complete control over the jogging action. In this circuit, pressing the start button will cause the control relay to energize. The relay will close a set of normally open seal-in contacts around both the start button and the jog button. Pressing the jog button will directly energize the starter coil. This method is intrinsically safe and is the prevalent method of jogging employed by industry today. A timing relay is similar to a control relay with one exception. Some or all of its contacts are designed to operate at adjustable intervals or lags after the control is energized. Time delay logic is an important function of control circuits. It allows a circuit to pace itself. Basically, there are three types of timing relays: dashpot timers, synchronous clock timers, and electric timers. All of these accomplish the same task, but they accomplish it by different methods. There are two categories of time delay logic. They are on-delay logic and off-delay logic. The on delay is designed to activate its contacts after a preset time has elapsed. The timer coil must be energized to begin the timing period. An on-delay timer will have two types of contacts: normally open timed closed and normally closed timed open. The off delay is designed to operate its contacts in response to the closure of an initiating switch. Closing the switch will cause its normally open contacts to close instantly, and its normally closed contacts will open instantly. As long as the initiating switch remains closed, the contacts will remain in their active state. Opening the initiating switch will begin the timing sequence. After the time lag, the contacts will return to their normal state. Off-delay relays will have normally closed, timed closed, and normally open, timed open contacts. The diagram shown above is a typical application for an on-delay timer. When the start button is pressed, both the control relay and the timing relay are energized. The control relay is necessary to accomplish seal-in. When the timing relay times out, the normally open, timed closed contacts will close and energize the coil of the motor starter. In this application, an on-delay timer is used to sequence a motor off after a time lag. When the start button is pressed, the motor starter will energize and seal in. Closing the seal-in contacts will allow the stop button to then be operational. If the stop button is pressed, both the control relay and the timing relay will energize. After the time lag has elapsed, the normally closed timed open contacts will open, de-energizing the entire circuit. The emergency stop button is necessary to disable the circuit without the time lag. Circuits such as the previous one sometimes react so quickly that they will inadvertently restart due to the reclosure of the timing contacts before the seal-in contacts have time to open. In these cases, it is sometimes necessary to connect a non-electrolytic capacitor in parallel with the timing relay coil. While the timing relay is energized, the capacitor will store a charge. When the contacts in rung 1 open, de-energizing the entire circuit, the capacitor will discharge through the timer's coil. This will keep the normally closed timed open contacts open long enough for the seal-in contacts to open. Off-delay relays are used in applications that require a circuit to operate in response to the absence of a signal. In the diagram shown above, when the float switch in rung 1 closes, the normally open timed closed contacts in rung 4 will close and energize the starter. As long as the float switch remains closed, the timed contacts will remain closed. When the float switch opens, the timing lag will begin. After the preset period, the contacts will open and de-energize the starter. This circuit uses an off-delay relay to turn a motor on for a preset period. The start button will energize coil M1 as a normal 3-wire control. When the stop button is pressed, it will de-energize M1 and it will trigger the off-delay relay. As the stop button closes the initiating contacts, the normally open, timed open contacts on rung 4 will close. This will energize coil M2. The timed contacts on rung 4 will then open after the preset time lag. Note, an emergency stop button is also used.